This is example 6-1, a jet against a surface. So we can see we have a hose here or something that's emitting a jet of water against this inclined surface over here. So part of the water is going to go up, part of the water is going to go down. We're going to assume that none of the water goes side to side, so inside or out of the page, just so we can actually make our calculations. All right, so we know we're looking for a force, or I said we should probably read this, right? So in the end, it's asking for us what the normal force is on the surface. So perpendicular to our surface here. If we want to find forces, then we'll have to do a free body diagram. In this case, we'll do a free body diagram of our water. So something like this. Right, that's going to be our free body diagram. So let's draw that over here a little clearer. So we have our water coming in and kind of goes up. That's the back of our little piece of metal there or something. Maybe the other one's a little thicker. And then it comes in, right? So this would be our free body diagram where this is C, this is A, and down here we have B. Now what are we looking for? We're looking for the force, the normal force, right? So we'll have a normal force going against this. Of course, we also have a tangential force. We can draw that in. That'd be Ft for tangential. But it says that we should assume that that's 0. Now, last, we want to give ourselves a coordinate system. Now, we could go with the usual x and y coordinate system, but in this case, we just want to have the force in the direction, this normal direction, then we'll draw ourselves a little coordinate system that fits into that. So we'll do something like in the normal direction and the tangential direction. This is our coordinate system. We'll say this is the direction parallel and this is the direction perpendicular. All right, I think that is all we need. Maybe we'll sketch just in that we know what this angle is. That's 45 degrees. Let's make that a 40. It looks more like a 90 here. 40, so it looks like a 90. For some reason, this wants to be 95 degrees. 45, there we go. All right, so I think with that we have all we need, and we can start doing our calculations. Now we know this water is moving, right? So we'll have to use our linear momentum equation. To do that, we'll have to know all the velocities. So we know the velocity at C, that's given to us as 4 meters per second. But we don't know the velocities at A or at B. So what we'll do is we'll use Bernoulli from something from here to there. So we'll have a streamline like this. And then we'll do the same in the other direction, going down, right? So we have those two streamlines. So we can say let's go to blue. Comes up a little better. So we'll say Bernoulli. But we'll put some extra stuff in there already, right? We're going to say, well, this is not a very, the elevations between where A and B and C are going to be very similar. So we say Bernoulli neglecting elevation change. Right, that basically means that ZA is equal to ZB is equal to ZC. And we also know that all these are in contact with the atmosphere. And everything in contact with atmosphere. You might remember anything that's in contact with atmosphere, it's atmospheric pressure. We're talking about gauge pressure, so we can set those to zeros. So if we then write our Bernoulli equation, right, then we know that the first pressure term is going to be 0 because we're at atmospheric pressure. We know what VA is, or in this case, VC. I got my stuff mixed up here. So VC squared over 2G. Right? And then my elevation term is going to be 0. And then if I go to A, which was the top one up there, right, then I can say that's the same. I'm going to say the pressure there is 0. VA squared over 2G. And then for the elevation term is also 0. Now that means that I can say VC squared is equal to VA squared, right? Because I can just multiply by 2G, which of course means that VC is equal to VA. All right, so this is looking at the streamline that goes from the tip of my hose upward. Now I can do the same thing for the hose going downward. Nothing's going to change other than instead of A, I'll have B, right? So without going through the whole steps again, we can say that the same logic applies. So maybe we'll say same reasoning for C to B, which means we can say VA equal to VB is equal to VC, and so all the velocities are the same, we'll just call them V. Okay, cool. So now we have all the velocities, so we can start writing our linear momentum equation. So let's write the full linear momentum equation. Linear momentum equation. What do we have? We have the sum of forces, this is a vector, is equal to d dt, integral over the control volume of the velocity, which is a vector, times the density, is a scalar, times the change in volume, dV, plus integral over the control surface, or the control surfaces. We'd have V, which is a vector, we have rho again, and then we have V dotted with dA, which are both vectors. All right, so that'd be our linear momentum equation. Now the good thing is that we can simplify this, right, because this looks somewhat daunting. So we can say the first thing we know is we have steady flow. So I'll say for steady flow and ideal fluid, we have water, and let's say uniform velocity profiles. All right, based on these things, we can simplify. Steady flow and ideal fluid, right? Ideal fluid means inviscid and incompressible. So if it's incompressible and it's steady, then the volume is not going to change. So our first term is equal to 0, right? So we can say sum of forces equal to 0. Now the second part is not going to be 0 because we flow across the control surfaces. But we can say, if we're going to say that we have our velocities are uniform across our control surfaces, right? That means we have that same profile. So that means we can just multiply instead of integrating. So we can say that's then equal to the sum of our velocity vectors times rho times the velocity vector dotted with my area vectors. right? That would be my equation then. And that we can now look at our very specific case. All right, so in our specific case, we have 3 control surfaces. All right, we have a control surface, I'll do the red right here. All right, we have a control surface here. We have a control surface there, control surface there. We think about this just like we talked about when we talked about control volumes, right? Then we have to define what the area vector is. In our case, the area vector still is positive outward. Right? So we'll have there, there, and there. And then also we have the velocities. Right? So velocity here goes inward, there goes outward, and there goes outward. Why is that important? Right? That's important because when we do the v dot a calculation, right, that means if they're in the same direction, it's positive. If they're in opposite directions, there's negative. So we'll note it's going to be negative at C and positive at the other ones. So that, what does that leave us? That leaves us, we go back to blue here, right? That means we'll have a vector, our VC vector, times our rho, and then this multiplication here, right? So we said in C, that where the inflow is, it's going to be negative. So we can say times minus VCAC, and then the other two are going to be positive, right? So we'd have VA rho VA AA plus, plus VB rho VB AB. That's very important to remember that those two, like one is a vector, like VC is still a vector, whereas the VC that we have, like that, the non-vector form is just the actual flow velocity. Okay, so this is of course still a vector, right? We have a vector here, and each of the velocities is a vector. So basically, in 2 dimensions, well, we have 2 of these equations that we can write. And in our case, we said we're going to write them in the perpendicular and in the parallel direction. But for us right now, we really only want to write it in the perpendicular direction because we're only interested in the normal force. All right, so we can take this and write this in the perpendicular direction. So we would get sum of forces in the perpendicular direction is equal to, let's first do the part that we get from our momentum, and then we'll see what we get from our free body diagram afterwards. So that would be equal to, let's see, we have it up here, right? So VC, let's go and look at it. If you think about it as a vector, it's going to be fully in the direction here. It's going to flow in this direction, right? Left to right. Our Fn was positive in this direction, so it'll be negative. Right, so we have minus, let's call it VA, and then perpendicular, times rho times minus, times, this is not A, go back here, getting myself confused. Let's write our, let's see what our flows look like here, right? So my flow in C, not a whole lot of space here, maybe here. Right, so I have my flow that's going in that direction, which means I have the 2 components like that. So it's going to be negative, all right. So it's minus VC. But VC tangential, perpendicular, and then we said it is minus VC AC. Then in our other directions, right? Let's just write those in, and then we can figure out what they are, what those components are. VAAA plus VB perpendicular VBAB. All right, so what does that equal to? Well, that's equal to, if we look at our free body diagram here, right, then the only force that's acting in the perpendicular direction is Fn, and it's pointing in the same direction as our coordinate system, right? So it'll be equal to Fn, which is the number or the value that we want to find. But let's continue with what we have here, right? So we'd have minus, these two minuses cancel each other out, right? So we'll have won't have a minus anymore. VC perpendicular, we already said this, right? Kind of the little arrow that goes up here, which means that not the full VC, but only the sine of 45, right? So we can plug that right in. So that would be the full VC times sine of 45 is square root of 2 over 2. And then we canceled out those negatives, so it's just VC AC. Then at A, there's no flow in A that's going perpendicular, right? That's 0. And there's also no flow at B going perpendicular, right? Because the full flow goes in the horizontal direction, in the parallel direction, right? So you can say that's plus 0, plus 0. That makes it nice. Didn't even have to think about exactly what the velocities are in that case, I guess. Which then means we are left with the VC's here, that we can put them together. We said we call them all V, so we'd have square root of 2 over 2 V squared times AC. AC is, of course, up here. It has a diameter of 100 millimeters, so it's a circular cross section, so we could say that is square root of 2 over 2 V squared times pi over 4 times DC squared. And I think with that we have everything that we could need, so let's plug those numbers in. So it'd be square root of 2, 4 times 2 is 8, times the velocity coming in was 4 meters per second. Let's not forget that we need to raise that to the second power. And then times pi. And then times DC, that was 100 millimeters. So 0.1 meters squared. And if I plugged it into my calculator, I get 88.8 88.858 Newton, or if I round it to three significant digits, I get 88.8 Newton. And I have my Fn up here somewhere. Excellent. So that gives us the force that we're looking for at 88.8 Newton. It makes sense, right, that our normal force will be pushing against this because we're shooting the water against that little plate. So overall, it seems to make sense to me.